cloud. Okay, B is this matrix with 2 to 1. You can check that they end up being the same, A, B, and B. Oh, sorry. Okay. Yep. And also sometimes it is commutative if B is a scalar matrix of the identity. So you can also check, I did an example where B is the identity times 2. So 2 on the diagonal, you can multiply it out and check that they are the same. Okay, any questions on this refresher? Okay, just a note is that for the transpose, you look at each row and each row becomes the column of a transpose. So like the capital T thing is just meaning transpose. So you go, this row becomes this column. Then you write the second row as the second column, third row as third column. Sometimes in the prep quizzes or practice problems, Bryce tends to write like a vector as 1, 2, 3 transpose. That's just because he doesn't want to format it as like a vertical thing in the canvas. But yeah. Okay, so let's do an example. Okay, so this, when I say like RQ, by the way, this is from the recitation questions, which I just showed you on Grace's website. So the first question is compute the matrix multiplication and think about how you might be able to arrange things. So we have this matrix multiplication. And I'll give you guys a sec to think about it. How do you think we can rearrange it in a way that's easy for us to solve? And you can feel free to raise your hand or shout. Yeah. So usually if you were to multiply this matrix times this, you like actually multiply it out, add each thing. But is there another way to write it so that you're not actually multiplying each thing, adding, multiply, add, multiply, add? Yeah. And maybe to help you, you can actually like write out what you would do to actually multiply it and see if you notice any patterns when you're writing out every term. Yes. Each row in the column. Yes. Yeah, that's exactly correct. So what happens is that like each term here, you move in front of like the first column. So you do -1 times the first column plus 1 times the second column, which is 1, 2, -2, plus 2 times the third column. So 1, 4, 0. And you get whatever answer it is. Why does this work? Because if you were to actually multiply things out, how do you multiply things? How do you do matrix multiplication? You do 0 times -1. So you have -1 times 0 plus your purple 1 times the second term, 1 plus the pink 2 times 1. And what happens is that you're always going to have a -1 over here, and then whatever number this is, you're always going to have this +1 here, and whatever is in that column. And you're always going to have the 2 here, and whatever's in front of that column. So you can actually like write it out as each term, and notice that each like row ended up becoming multiplied by whatever column it was. And so you get your answer. Any questions on that? Okay, so next is something about like row reduction and finding solutions to AX equals B. Okay, so you might not necessarily need to know what row echelon form is, but I think it's important for understanding when you're row reducing, when do you stop to find a solution. So what is row echelon form? Row echelon form means that all rows of zeros are on the bottom. So if you have any rows of zeros, they have to be at the very bottom. Any non-zero rows should always begin with a leading 1. And wait, sorry, wait 1 second. Okay, yeah. And then the leading 1 of a row should be to the right of the leading 1 in the row above. What does that mean? So for example, this matrix here, this is in row echelon form because you can check that all rows of zeros are on the bottom here. Where there is a leading 1, this, like the first number in this row is a 1 here. That's good. The second row that has wherever the first number is should be in the column after where your leading 1 in the row above it was. So the 1 should be here. However, something like this, 1, 0, 1, negative 3, 0, 2, something like this would not be in row echelon form because the row of zeros is not at the very bottom. Okay, and another example, what if we had like 1, 0, 3, 0, 0, 1, negative 2, 4. So we see that the first term with a number is in this first column. That's fine. That means that in the second row, wherever your first number shows up, it should show up in the second column or later. And it does. It shows up in the third column, which is after the second column. That's fine. So it works, and this is in row echelon form. However, something like this, 1, negative 2, 8, 3, 1, this you see is not in row echelon form because here you have a leading 1, but here you also have another leading 1. Whatever is at the very top, like the leading 1s should go down the columns. They shouldn't go like the other way. So in order to make this be row echelon form, you would want to row reduce by switching those rows. Then you would have a leading 1 at the top, and it would be in row echelon form. Okay, and then a further a further reduced form is a row reduced echelon form. So that just means that it's in row echelon form, and any column with a 1 has to have zeros elsewhere. So you don't always have to do this, but I find that sometimes if you like row reducing better than like directly trying to solve something in this form, it might be easier to have it in row reduced echelon form. And I'll show you why in a sec in an example. So here, the identity matrix, that's in row reduced echelon form. The leading 1s are all in the column behind it. And yeah, everything else, here's a leading 1. Everything else in that column is a 0. Here's a leading 1. Everything else in that column is a 0, and as well as this. Another example is like this matrix, which that is also in row reduced echelon form because you have a leading 1 here. Everything else is 0. The other leading 1 is a column behind it, and everything else in that column is also 0. But something that is not in row reduced echelon form is something like this, because here's a leading 1. Everything else in that column has a 0. However, here you also have a leading 1, but not everything in that column is a 0. So that is not in row reduced echelon form. And a nice term to know is what I'm going to refer to as the rank. So the rank means like how many leading 1s do you have, or how many like pivots here, like this 1 here and this 1 here. How many leading 1s you have, or it can be some other number if you didn't reduce it down all the way. Okay, any questions on these definitions? Okay, and can everyone hear me okay? Okay, did you have a question? Okay. Okay, so now let's get to the important part, solving linear equations. So there's 3 types of row operations. First one is you can switch 2 rows. The second one is you can rescale a row. So you can multiply the row by something else. And the third is you can combine rows. So add a multiple of one row to another. And when we solve these systems of linear equations, we're gonna see some pattern. And so I made this nice chart here, which tells us based on the rank of your matrix, like it will tell you how many solutions you have. You have 0, 1, or infinity. And we can also think about how the determinant could also help us determine if there's solutions or not, or infinity. Okay, so let's actually do a row reduction and back substitution. Okay, by a raise of hands, how many people want to do this on their side, like are comfortable doing this on their own now? Okay, so okay, why don't you guys do it and then we can compare. So I'll give you guys like 3 minutes. Okay.
So what are we meant to do?
Solve this equation, solve this system of linear equations for x, y, z. So your answer should be like x, y, z equals something. Oh yeah. A template of them is right now, but I will post them after recitation. Yep. And you can like talk amongst yourselves too if you want. You have to work alone. So if you go to my website under the 114 tab, they'll be under my live recitation notes. So right now the template is there. That's here where it says template. And I'll also post like the full version with all the answers there also. But my live recitation notes, so like what I write in person will be in the live recitation notes. Okay, so if you're not finished, that's okay, but let's just get started on like going through this. So, okay, I already wrote the first step there. So I guess the first step is you want to make this as an augmented matrix, right? So when you're converting this to a matrix, make sure that like you don't just blindly write down these numbers like 4 to -1. Like what if they had written the third equation as 2y minus x minus 5z equals 1, and you had just blindly written down the numbers, you would have written 4 to 2, which would have been incorrect. So make sure first that all your variables are lined up before you write it in a matrix. Okay, then we want to make this into an augmented matrix. What does that mean? You just rewrite the matrix again and add this like answer, this 2, 1, 1 here as your last column. So now you have an augmented matrix, which just means it's like a big matrix. Okay, all right, so due to time, I'll just like go through what I did first. So the first step I did is I did the first row. So the first tip that might make things easier is if you always have a 1 in the top left corner. That will make things a lot more easier so that you can cancel anything that needs to be canceled out. So I changed R1 to R1 times a 4. Oh, a 4. That gives me 1 -3/4, 1/4, 2/4. And I write down the rest of the numbers the same way. The next step I did is here's a 2. I want to get rid of that 2. How do I get rid of that 2? I could change R2 so that it's the second row minus 2 times the first row. And so the first row stays the same. But now the second row, 2 minus 2 is 0. 1 minus -3/4 is 10/4, and so on. So let me keep writing this. Okay, now in the third row, we want to get rid of that -1. So we do R3 equals R3 plus R1, so that we can get rid of the -1 there. And we end up with this augmented matrix. 4, 3/2. Okay, and then the next step I did was, now we have a number here, a number here, but we don't want this number here, right? Like the leading term should be in the column to the left or to the right of it. So how do we get rid of that term? I could do R3 equals R3 minus half R2. And that gives me this matrix here. 1/2, 0, 3/2. Okay, to make things easier for ourselves, I don't want to deal with fractions, so I just remultiplied this by 2/5, and also the third row, R3 by -6, just so that I don't have weird fractions or as many as I want to deal with. Oh, sorry. 0, 1, 1, 0, 0, 0, 1, -1/4. Okay, so now, can anyone guess what form this matrix is in? Like row reduced or row reduced echelon form? Row reduced, yes. The REF, not RREF. Yep. So yeah, it's in row echelon form. Wait, okay. Well, it's in row echelon form. So at this point, you could stop here and you could solve it. Sure. So what do? This first column represents x1. Second column, we can call it like x2. Third column, we can call it x3. So looking at each row, we now write our new equations. The third row gives us the equation x3 equals -4. The second row gives us the equation x2 plus x3 equals 0. It's like 1 times x2 plus 1 times x3 equals whatever constant you have over here, 0. we know what x3 sub 3 is. So x2 minus 1/4 equals 0, or x2 equals 1/4. And then in the top here, this first row gives us x1 minus 3/4 x2 plus 1/4 x3 equals a half. You plug in what we found for x2 and x3, and you get that x1 equals 3/4. Okay, so hopefully, yeah, question?
I mean, I know we're studying matrices, but wouldn't it be easier to just solve simultaneous equations if you just put it all into the equation form?
Like elimination or like substitution, you mean?
Yeah, like simultaneous equation, you have three simultaneous equations, and you just solve them. Or do we have to use the matrices?
But how would you solve three simultaneous? So like if you have two variables, then yes, like if you have like 2x plus y equals 3 and 2x minus, oh, sorry, minus 3y equals 3, you could use elimination and solve it this way. You get like y equals something, right? That's the standard way. But right now we have three variables. How would you?
You would reduce it to 2 and then.
Oh yeah.
I mean, it's literally the same thing.
Yes, it's essentially the same thing, but it might take longer. Because you would need to use these two to reduce it to some equation with two variables. Then use these two to reduce it to an equation with two variables. Then use both those equations to do this way to get one variable. Then go back and back. So the matrices way is simpler, or like quicker sometimes, because imagine if you had way more complicated things here. Okay, any other questions? Okay, so here we stopped at row echelon form. But what if I wanted to keep simplifying this to row reduced echelon form? So I'm showing you that it doesn't matter what way you do it as long as you get the answer. But we could have either stopped at row echelon form, got the answer x1, x2, x3. Or we could have taken this matrix and kept row reducing it to row reduced echelon form. So we could take that and I'll just like write what it ends up being reduced to. It ends up being reduced to this. Now you can see why row reduced echelon form is much nicer, because look, we got the identity matrix. What does this mean? From the third row, we get directly x sub 3 equals negative 1/4. From the second row, we directly get x2 equals 1/4. And from the first row, we get x1 equals 12/16, or 3/4. So if you just row reduced one step further, you get like, you could just directly write your answers. Okay, something to notice that I want to point out is the rank. So if we look at this matrix A here, what is the rank of A? You can shout out. Rank is how many leading ones do you have? 3, right? If A is just these 3 columns, how many leading ones do you have? 1, 2, 3. So rank of A equals 3. Now, the augmented matrix, I'm going to call like A flat. What is the rank of A augmented? You still only have 3 leading ones. There's no leading one here. So it's still 3. Okay, so we saw that both ranks were the same and we got one solution. That's something to notice. So one solution is if we get one solution if the rank of A is the same as the rank of A, the augmented matrix. So let's go to our nice table. We just saw that if they are equal, we have one solution. Okay, let's do example 2. All right, so I'll give you guys like 3 minutes again, and I'll ask you guys for an answer this time. So we won't go through everything. All right, does anyone have a solution yet or an answer? You have an idea? Yes. Yeah. So did any, oh wait, I probably should have said it. Who thinks there's no solution? Okay, well the answer is no solution. So okay, instead of like writing it all out, let me where do I have it? So yeah, you can row reduce it. So here I made an augmented matrix. Row reduced it, row reduces to this matrix, this augmented matrix. What does that mean? Well, remember this first column is x1, then x2, then x3. The third row is telling us 0 times x3 equals 2. How do you get 0 times something equals a number? 0 times anything is always 0. So this is not possible. 0 is not equal to 2. So you can't get a solution from this. There's no solution for this augmented matrix. Now something to notice is that if we take a look at A, the rank of A is 2 because there's 2 leading ones here. This is -1, but if you multiply that whole row by -1, this would be a +1. So you have 2 leading ones here. The rank of A is 2. The rank of the whole augmented matrix is 3 because this 2, if you divided it by this, if you divide the whole row by 2, this would end up giving you 1. And so you'd have 3 leading ones for the rank of your augmented matrix. So we just saw that if the rank of A is less than the rank of your augmented matrix, then you got no solution, right? No solution. You can also notice that if you just look at A here, the determinant of it is 0. A nice fact about determinants is that if you ever have an upper triangular matrix or lower triangular matrix or diagonal matrix, the determinant is always the diagonals multiplied. So that's how I know it's 0. Okay, any questions on this example? Yes.
What is the determinant?
The determinant is something that you'll use to see if an inverse exists. It's just like a property of a matrix. You can think of it like that. Yes.
Before, like another question, you said that you went from like row reduced form to row echelon form.
Yeah.
How did you do that? Yeah. You have that
Yes. Okay. So we ended up with row echelon form here. And then if you keep doing row reduction, so this is the matrix we ended up with at row echelon form. Then if you take row 1 minus a fourth of row 3, it simplifies to this row here. And then you do another row reduction. So like row 1 is row 1 plus 3/4 of row 2. And then it ends up simplifying to this. So it looks like the identity. Yeah.
The steps you're doing to row reduce,
Mhm.
You have complete flexibility in choosing which row to reference.
Yes. Yep.
Then how do we know that it's not just a mistake in our references that we came up with 0, 0, 0? Maybe there was another row we could use. You know, is there like a methodological steps we can use to make sure we're doing the right operation?
I think the first step you should do is try to get a 1 in the upper left corner. Then from there, start trying to get like eliminating any terms here. Then go to the next column and try to eliminate any term here. Yeah. So there's no like it's just like you can do anything you want as long as you get like what.
Is there ever a moment where you could maybe incorrectly get 0, 0, 0 and then find out it's no solution when there is a way to actually get a solution?
If you make like an arithmetic mistake, then yes.
Okay.
Yeah. Yes. Yeah, you can solve it either way you want. So you can either stop at like here, Grice did the triangle way, but notice that here we had to do these other equations like x3 equals -1/4. Then you have to do each row and try to solve it. Or you could just keep on row reducing and then you can directly write them. So either way works. Any other questions on that? Okay, so for the third example, because we're short on time again, and I'm pretty sure you're all tired of row reducing. So here's the third system example that I wanted to show. It row reduces to this matrix, augmented matrix here. What I wanted to point out is that this last row, they're all zeros. So you get 0x1, 0 plus 0x2 plus 0x3 equals 0. There's no contradiction there. It's fine. You have 0 equals 0. So what does that mean? Well, the second row, what does that give us? That gives us this equation here. The first row gives us this equation. So right now we have 3 variables, but 2 equations. And specifically x3, there's no limitations on x3 because the third row didn't give us anything. So x3 can be anything. x3 could be 1, then you get a certain x1, x2. x3 could be 2, then you get a different x1, x2. So for this system specifically, there's an infinitely many number of solutions. How do you actually determine what this is? Well, right now, x3, we said it could be anything. So we can arbitrarily let x3 equals t, like some variable, right? So now we want everything in terms of t. The second, the purple equation, 6x2, if you add 10x3 to both sides, you get plus 10x to 3, but we said x sub 3 is t. So 6x sub 2 equals 10t, and x2 equals this. Same with the pink one, we can substitute x sub 3 with the t's, and we get x1 equals 2/3 t. So this is infinitely many solutions where t can be any real number. Something to notice here is that the rank of A was 2. Rank of A augmented is also 2. So rank of A is the same as rank of augmented. How does that make it different from our first example? Well, notice that there's 3 columns, but we said the rank of A was 2, rank of A augmented is 2. In the first example we did, here, I guess, we had 3 leading ones, and 3 was the number of columns we have. So maybe updating our chart here, we just saw that if the rank of A equals it, then we had infinite number of solutions, where like the number that they're equal to is less than how many rows you have. But if it's exactly equal to how many rows you have, that's like the first example where we got 1 solution. Then the second example is where the rank of A was less than its augmented, so 0 solutions. Okay, any questions on that? Okay, so let's see. Whoops. Last thing, so when you're solving ax equals b, there's 2 methods right now that we know of. One, you can write it as an augmented matrix, row reduce, back substitute, you get an answer, x equals something. A second method that you may have seen in Grace videos is this thing where you have ax equals b. If you multiply both sides on the left by A inverse, you get A inverse ax equals A inverse b. This A inverse A, by definition of what it means to be an inverse, it equals the identity. And the identity, you can kind of treat it as like a 1. So it's just saying that x equals, if you can find its inverse, you can just do the inverse times b, whatever vector was over here. So either method works when you're solving a system like this. Any questions on that? Okay, quick thing about inverses. So inverse, I said it has the property where A times its inverse is the identity. Of course, inverse only exists if it's a square matrix. So it has to be a square matrix. If you have a 2x2 matrix, this is the formula for how you find the inverse. But if you have a higher dimensional matrix, like a 3x3 matrix or 9x9 matrix, how do you find the inverse? So what you want to do is write a big augmented matrix with A on the left and the identity on the right. So like if your matrix A was like 2, 3, 5, 6, 7, 8, 9, 10, 11, then you'd have a 3 by 3 identity on the right side. Row reduce it so that eventually you get the identity on the left side, and whatever is left here on the right, that will give you what your inverse is. So this is how you find the inverse of a larger size matrix. And I did include an example here where you have this weird matrix, you can row reduce, and you do get the identity. And how you can check, now you can check if you did your row reduction correctly, because you can multiply this matrix by A and see if you get the identity. Then you'll know if you row reduce correctly and you found the correct inverse. Okay, any questions? Yes. I don't think so. It should exist. All right, recitation is over. Thank you guys. See you next week. Yeah.
So like the one that I see that you said that like for inverses, all the rows have to like be reducible.
Identity is just.
Uh,
Versus this.
Uh-huh.
It says that just that because of the whole like